the second second lecture of Sergei Gukov, topology generic Q. Yeah. Okay.
Yes, that's right. So I'll be using this whiteboard. We're continuing from last time, and this will make it easier for you to follow on your own. So maybe I'll quickly share the screen in case if someone is still tuning in. So last time we ended, I just want to remind, we ended with the definition of this integral. I'll call it z hat. It's a multiple integral over as many vertices as we have in a graph. So imagine that you have a graph, or for simplicity, a tree. So we introduced adjacency metrics, we introduced these integrals. So a priori, they have nothing to do with topology, but now and basically in the rest of this lecture and most of tomorrow, we'll be exploring this object, trying to answer the kind of question, what object is this and where does it belong? So as Jan pointed out, some of this building blocks, which are easy to play with, are a little bit ad hoc. So I wrote ingredients that you would associate to each vertex or edge of the graph before integrating. So natural question is, where do they come from, and why would I care about this particular powers of Q, for example, appearing, or this specific form? So exactly this question we have to slowly answer today, and I imagine that some of part tomorrow will be devoted to this. So first, in the last lecture, I wanted to make sure that the definition is clear. So that's the definition of this bunch of integrals associated to graphs. And definitely at this point, I'm on the concrete side of the dial. So we'll talk about conceptual things later, but I think to make sure that everybody is following, I want to be as concrete as possible, and this make sure these integrals are well defined, easy to compute, and motivated in part by that. So I'm going to experiment with computing this integral. So we already made some preliminary statements in the theorem that I started, but we'll continue with several other bullet points and fill in the rest of the statement. But I also want to now look at these integrals more precisely. So this short Mathematica file, and there are many more circulating over the internet which do the same thing for this table of integrals, does the following. So first, it starts with the definition of the graph. I'll share the notebook with you after this demonstration. So we can input the graph, you can input this integer labels. I think we call them AI in the first lecture. First, it computes adjacency metrics. That's what we call Q in the lecture. Verifies that it's negative definite, for instance, computing eigenvalues. That was useful for a naive definition, which we'll improve shortly. And then basically it computes the value of the integral itself. So that's the kind of second chunk of this file. As you can see, it's pretty short. It's not a sophisticated Mathematica code, but let me just try to run it for you. So evaluate notebook, we'll see what happens. So it quickly goes through the computation, and yeah, here is the answer. So what we see from here is that for a particular graph, which we're showing at the top of the file, what we get is some Q series. I truncate these powers by power of Q, which is 300. When you play with it yourself, you can truncate it at 1000 or 50, whichever you prefer. What we see is that the answer looks like a power series in Q with integer coefficients, which are not necessarily positive. We already see that there are some minus signs. And apart from this overall prefactor square root of Q, all the powers are integers. So as we first meet a new person, we slowly learn about that person, asking questions where you come from, basic characteristics, age, interest, and so on and so forth. Same with this gadget. So with a bunch of these integrals, we'll slowly learn who they are. So therefore, one observation is that they seem to have this integer powers and integer coefficients up to this overall power. And now let me experiment a little bit and ask the question, how does it depend on a graph? So how it depends on Q, we already kind of see it's a Q series. But let's ask how it depends on the graph. And for this, I'm going to change my graph. So here it had 4 vertices with these particular labels. So I'm going to add another vertex. I'll say that vertex 4 now will be connected to another new vertex 5. And I'll modify this coefficients accordingly. So I added another vertex, added another coefficient. And here what I did, I copied the previous answer, saving it just so we can compare the result to later. So let me see if I can increase the font so it's easier to see. Maybe, let's see, does it work? Yeah, only a little bit. So font, how about we increase it further to something even more visible? Okay, this is much better. So now what I'm going to ask for this new graph, I'll ask Mathematica to forget everything that happened before. Here we go. And I'll ask Mathematica to do a completely new calculation. So every time I do it, I have to say I'm a little nervous because what if something goes wrong? But anyway, so that's our new graph. So previously it was 2, 3, and here it was 7. So I changed it to 8 and added a new vertex. So now it's a 5-fold integral. So there are 5 vertices, 5 integrals to do. And we see that eigenvalues are still negative. We're in a good shape, no problem here. Right, and that's a new answer. And the previous answer is saved, so you can see it didn't actually change. So what's happening is that our integrals are not really attached to graphs, but they're really attached to equivalence classes of graphs. So I can repeat this exercise. So for instance, add yet another vertex, say 5 now will be connected to 6, for instance, and I'll repeat this game. Maybe just one last time. So I'll change this to 2 and 1, for instance. So we'll ask Mathematica to forget everything that happened. And I'll do the computation one more time. Probably the last time. So now the graph has how many? Let's see, 6 vertices. So these are some of these integers and so on and so forth. So the answer is still the same. So it doesn't change. We keep changing graph further and further, but the answer remains the same. And again, please keep in mind the structure. So we could play with it a little more. You can
So
put
the
for.
graph doesn't
Can I ask a question? If
no,
I take
no
the
loops in the graph, yeah, Sergey. So because it's all kind of like Dinkin diagram of type D or something. So what is you probably will explain what is relevant.
Yeah, so it's tempting. Absolutely, it's tempting to do. Actually, since you asked, this is not quite Dinkin diagram because these labels are not -2s, which what we would see for or ones for Dinkin diagram. But yeah, you
that
can
was exactly my question. Just to take the -2, so that's the negative of the Dinkin, the adjacent, the Cartan matrix. So that gives the root, just the negative of the root lattice So what does this integral really mean in that case?
Well, let's do that. So it's a fun exercise. So then I'll have to change it quite a bit. So let me do E8. Okay, so that's probably the easiest. So 1 goes to 2, 2 goes to 3. Then I'll say that 3 goes to 4, and also 3 goes to 5, 5 goes to 6, 6 goes to 7, 7 goes to 8. So there should be 8 vertices. All of the coefficients label should be -2 or 2. That depends on convention. One thing I shouldn't make a mistake on is putting 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So it's a bigger graph. It has 8 vertices. And again, we're doing this kind of experiment in real time. You see that I'll share with you this notebook so you can play with any graph you like. So indeed, you may suspect that something nicer may happen for if it's a dinking diagram of a root system. So let's again ask Mathematica forget what just happened before. Otherwise, it wouldn't be a fair computation or exercise. So let's ask to do this one more time. Well, we see the Cartan matrix of E8. That's adjacency matrix. That's good. Let's see. We see that it's again negative definite. That's looks right. Sometimes I put this additional valency 3 vertex in the wrong place, so you can double check that I did it okay. So we have 8 vertices. E8 looks okay. It's a bigger matrix, and that's the answer. That's the result of the computation. So I'll try to enhance it again one more time. So let's see, maybe this font will be better. This showing up too small. So let's see. How about maybe this? Okay, this is better. So first of all, you see that overall power is definitely off. So it was square root of Q rather than Q minus 3/2. So that already changed. So then let's look at the detailed structure of the Q series. It also changed. So we had 1 minus Q, that seems to agree, but then before we had minus Q to the 5 plus Q to the 10, here we start getting something completely different. So actually this exercise showed that we did learn something, that it does depend on the graph. So it's not like we're gonna get the same answer, this one, all the time for every single graph. So it surely does depend, but also it sometimes doesn't change, meaning that there are equivalence relations. And next thing we need to discuss is what are these equivalence relations. I'll stop sharing this. I'll share with you the source so you can download it from my website. And again, there are many versions of this code. It's actually, since the definition was mathematically well defined and in fact fairly easy, as you'll see very soon, you can actually write the same code yourself. It's not a big deal at all. And again, today I'll try to decode why. So we'll learn a little bit more about the structure. But again, assuming no prior knowledge, we're just learning about this friend slowly. So I'll go back to the same whiteboard. And here is the link again. I'll also reshare the whiteboard. And now we'll go there. Yeah. So let me continue formulating this theorem. So it will consist of several bullet points that will summarize the basic properties of this gadget, of this class of integrals. And the first bullet point that I mentioned, which is actually extremely simple. Again, you can do a ratio test or more sophisticated techniques to quickly show that, first of all, this object is convergent in unit disk with respect to variable q. And it's clearly labeled by a co-kernel of the adjacency matrix that we noted already last time. So now I'll continue with other bullet points, and we'll come to this first bullet point a bit later. So we also saw, and you can prove that it's true in greater generality for completely general graphs, that it has integer powers and integer coefficients. So in other words, what we're dealing with, this fellow labeled by B and as a function of graph and Q, maybe I'll not specify this for a second. It has the following structure. It's Q to something fractional. Let me call this fractional power delta B. It's also labeled by B, of course, just like the entire series. And then it has coefficients C0 plus C1 times Q plus C2Q squared. So all powers are integer, and also the coefficients are integer. So in other words, this object lives in Z of Q, power series of Q, up to this Q to the delta B. So in the ring of power series. Now, that's again, what it's like with respect to Q dependence. What about dependence on a type of graph? So I'll make a definition in a second, but we saw that it's invariant under certain moves, under certain equivalences. So I'll keep writing and sharing the screen. So these moves have a name, and they appear in any good textbook on topology, in particular 4-manifold topology as well as 3-manifold topology, and they're called Curvy, 3-dimensional Curvy moves, or also in the context that we encountered them Curvy-Neumann moves due to Rob Curvy and Walter Neumann. And I'll give a definition of what these moves are in a second. Finally, to complete the theorem first, so that we only have one unfinished business to return later, I'll make the following statement, and again, we'll refer back to this theorem later on, that this object, as we saw, I could prove in first bullet point that it's convergent inside the unit disk, but not necessarily on the boundary where absolute value of Q is equal to 1. So anticipating connection to usual quantum topology, familiar invariants in quantum topology are usually associated with quantum groups at roots of unity. Natural question is, what happens when Q approaches a root of unity? For example, if Q goes to exponential of 2 pi I over K. So this is a typical specialization that's used in quantum groups to obtain many valuable invariants. We'll talk about this later on. And important part of this theorem, which was in some sense the main motivation, and that worked with Pei, Putrov, and Vafa, and later with Manolescu and others, is that at roots of unity, this new object gives familiar quantum group invariants. In fact, quite many of them. So invariants of 3 manifolds together with knots. If you, I mean, I won't discuss this generalization, but that's 3 manifolds to me will be more useful. So this is probably the first place where topology starts showing up. I don't want to assume much familiarity in these lectures with Kirby moves and things like that. So if you know this subject, then feel free to tell me to speed up, but I was planning to give a definition. So define what are these Kirby-Neumann moves. So since we started with graphs, so I have two things to demonstrate or explain. One, explain these equivalences, and these are going to be analogs of Reidemeister moves, which are perhaps a little more equivalent, familiar class of equivalences in the case of definition of knots, and then to explain what our graphs have to do with free manifolds. So that that will happen immediately now. So right. So what we saw in this short demonstration was a very specific type of move. So suppose you have a graph and there is a vertex attached to the rest of the graph. So then there are equivalences which are respectively called blow up and blow down, which allow you to replace this given vertex labeled by some integer a by creating an extra edge and an extra vertex labeled by ±1. So as you might have noticed in my equivalences, I only made those changes involving ±1s, but this label A that we had before should be changed accordingly. Namely, it should be shifted by either plus or -1, depending on what choice of sign you made for this newly created vertex. I didn't demonstrate the second type of move. So this is also called blow up and blow down, which you can do. Again, I shared the code, so I can actually even check explicitly that if you have two vertices labeled by A1 and A2 joined by an edge, this is in fact generic for any graph. So of course, any graph, as long as it's non-trivial enough, will have edges. So basically what it says is that there is analogous blow up and blow down operation, which does something extremely similar. It allows you to replace this edge by two edges and a newly created vertex, which carries label ±1. And just as before, you change A1 to either +1 or -1, and A2 to either +1 or -1, according to whether your choice of sign for +-1 was plus or minus. Okay, so this shows that these two moves are called blow up, blow down moves on graphs, and maybe I can now reveal the name that this graph and this context of Kirby calculus is called plumbing graph. So this is definitely like one class of relations which involves ±1 as newly created vertices. So there are a couple of more moves. So the list is not very long. It's not too complicated, and the other set of moves involves vertices, special vertices labeled by 0. So all you have to remember, if again this is the first time you see this type of Kirby calculus, is that you're allowed to create new vertices labeled by 0 plus -1, or if you see somewhere in your graph vertices labeled by 0 plus -1, then you can use one of these operations. So suppose you have, for example, disjoint union of various graph components. I'll call them gamma 1 and so on, gamma sub s. So this is disjoint union. So graph does not have to consist of only one connected component. Then you can perform another equivalence by joining them into gamma 1 plus gamma sub s. Okay, and you join all these fellows in a new vertex with label A, and here is label 0. So it actually is a whole class of moves which doesn't depend on A, quite interestingly. Usually it's used from right to left, not the way how I showed it, to simplify things. But it shows that a 0, unlike plus minus 1, vertex labeled by 0, is the one which is very destructive. It's basically something that tends to equivalent to eliminating the whole piece. And this is indeed illustrated also in yet another move. So here is another move that starts with vertex, which is a sum of two labels, A1, A2. In other words, you can take any integer and break it into sum of two other integers, and then claim is that it's equivalent to this. A1, 0, A2. So again, usually this move, this last move is used from right to left, where you see something with a 0 labeled vertex, and you can say that the whole chunk involving 0, everything that touches it gets eliminated, kind of like in the above. So, right, so these are, again, so-called Kirby moves, and you can either see by playing with them or, in fact, analyzing this integral that I showed you, analytically in complete generality, that it's invariant under this moves. So therefore, a very pragmatic answer to the question, what's so special about those choices that we made in constructing this set of integrals, we chose very special pieces associated to vertices and edges, parts of the integrand, in such a way that the result is actually invariant under this moves. That's perhaps the most important property. So if I made slightly different choices, if I chose different powers of Q somewhere, I think Jan asked about this, or if I made slightly different dependence on this variables X that we were integrating out, then we would miss this crucial property. So that's why everything was chosen in a rather special, careful way. So any questions so far? So
you will explain how it is related to the 3D topology, or?
Yeah, that's gonna be the next item. Yeah, that's right. So right, so that's why I think one of these bullet points in the theorem, bullet point number 3, basically means that what we got, even though it wasn't obvious from the beginning, is invariant of 3 manifolds, or at least this particular class of 3 manifolds. And I'll tell you next, so my next goal is to tell you what exactly is this class, how to generalize it completely. But we already start seeing that it is, I mean, that it's supposed to be invariant of 3 manifolds, because the way we do such proofs in topology, either in the case of knots, showing invariance under Rademeister moves, or in the case of 3 manifolds and 4 manifolds, implementing certain construction, and then showing that it's invariant under finitely many moves, which are in 4 manifold topology are called Kirby moves. And these ones, what we just encountered are, there are 3-dimensional avatars, sometimes called 3D Kirby moves. In the general case, there'll be slight generalizations of what I wrote, but in the case of this graph manifolds, that's exactly this Kirby-Neumann moves, which I summarized for you rather carefully.
Yeah, and knots or links, probably they are encoded where? just three manifolds or three manifold with knots?
Right. So they'll play double role. That's why. Okay, let me state the next theorem, and I'll come back to this question. That's a very good question. So in this series of few lectures, I didn't plan to talk about incorporating knots inside three manifolds. This can be done, and I'm not going to do it just for sake of clarity or lack of time, because it's only a few lectures, but knots will appear even in construction of three manifolds themselves. So next important ingredient from topology that I'll need is, and that will explain what just happened in the first lecture and until so far, is the following important theorem. So this theorem is due to Licorice and Wallace. Yes, and I'm going to add Curvy to the list for the reason which I'll explain in a second. So that's another important theorem, which says that every closed oriented three manifold. So this is our first series encounter with three manifold. Arises by surgery and more precisely integral Dane surgery. These are the standard names. Oops. On a framed on a knot, or more generally a link in S3. Oops. Okay, so my iPad lost connection. I'll just reconnect to finish the sentence. Let me call this link K, and this link sits inside 3-sphere. So there are several things that I have to unpack about this theorem. So first of all, we need the notion of knot or link. So knot is simply an embedded circle into S3. So typical examples, and also to introduce notations, are the following. For example, knots are often classified by how many crossings you see when you project them to a plane, and trefoil knot, which in the Rokhlin classification is 3-1, is this knot right here. I'm not very good at drawing knots, as you can see, but trefoil is perhaps one of the examples I can do. So that's the first non-trivial knot. There is no non-trivial knot with 2 crossings. Next one, there is only one prime knot with 4 crossings. That's called figure 4-1, or also figure 8 knot, because if you draw it properly, you see figure 8, and it looks as follows. So this is where let's see if I can if I can do that. Oops. It looks something like this. Maybe I need to change a couple of crossings, I guess. But anyway, let me not try to do it in real time. So this is basically how trefoil and figure 8 knot looks like. I'll fix it later on. And now link is basically an analogous by definition. A link is same thing with several components. In other words, it's a disjoint union of bunch of S1s, circles, embedded into S3. And a prominent or simplest example of this would be the Hopf link. Oops, Hopf link, which is this. So you see two circles linked together. Next interesting example would be Boromian rings. Which consists of three components, three connected components. So let me draw them as red, green, and blue, or I'll choose purple. And they have, I'm not gonna try to attempt drawing crossings, but they have an interesting property that every two components are mutually unlinked, but three of them are linked in a non-trivial way. So this indicates that there could be high linking numbers and so on. That's basically a lot of fun. But the point is of this theorem, so hopefully it gives you an idea of what a knot or a link is. And the point of this theorem is the following, that you can take any such knot. So let me again go back to the trefoil knot, since this is more basic and perhaps easy example I can draw. So I'll try to draw it like this. So the statement of this theorem is the following, that if you take a neighborhood of a knot, so the way it looks right now is imagine it's embedded in a three-dimensional space or a three-sphere by compactifying at infinity. So then we take tubular neighborhood of this knot. And since knot itself is a circle, then tubular neighborhood is going to be a solid torus. So in particular, this way we represent this three-dimensional sphere S3 as consisting of two parts. One is what's called knot complement S3 minus K, or link complement. I'm drawing it for not just for simplicity. Union over the two torus boundary of S1 cross D2, solid torus, right? So here, this three sphere, so we break it into two pieces, but then we can construct a new manifold out of it by performing so-called surgery operation. So we do surgery. If we keep the first piece unchanged, so in other words, I'll keep S3 minus K intact. But then we glue the second piece, the solid torus, S1 cross D2, via non-trivial global diffeomorphism of the boundary. So phi here, this var phi, is element in the mapping class group of the two-dimensional torus, which is the boundary, which is SL2Z, or more precisely PSL2Z. But I'm not going to worry about quotient by plus minus one. So such elements in SL2Z are naturally labeled by matrices. So let's think about matrix presentation. So it will be something like P, R, S, T, where PT minus RS is equal to 1, of course, and P, R, S, T are integers. And then the statement of, I mean, it's actually not hard to show that this result of the gluing construction of this so-called surgery does not depend on values of S and T here. So in fact, I can replace them by anything. So it's not going to be important what they are for the result. And what this gives is it gives so-called P over R surgery as a result. Now, definition that builds on this, and I'll write it a little bit to the left of this diagram, and that's what's used in the above theorem. Such surgery is called integral. Integral if R is equal to 1. So in other words, if it's labeled by a single integer p. And in general, such surgery is denoted as S3 P over R of a knot or link K. So that's the definition. Any questions so far? Right, so this theorem is about constructing free manifolds. So if we are to talk about invariants of free manifolds, we need some way of constructing them, and there are several. For example, an alternative option would involve Higger decompositions based on ideas from Morse theory. So I'm not going to talk about it, and this is just to give you an idea that there are different ways of doing it. This is a particular construction which has one interesting corollary.
Sergei, if you have a link, so you have kind of a product thing, so it does not depend on what order do you do the surgery or what?
That's right. If you have a link with several components, it doesn't matter what you, in which order you do the surgery. The theorem also says that you can formulate the theorem without mentioning the word integral, but so in other words, it can be more efficient if you allow this fractional P over R, so-called surgery coefficients. But a theorem says that you can always use Curvy moves to represent it as integral surgery. In other words, always you can find the presentation of a manifold using integral surgeries, and moreover, another remark I should make here is that presentation is highly non-unique. That's where the name Curvy comes in. So that's why I put Curvy in the list, because you need two things. You need A, construction, and B, invariants under certain moves. And these are the so-called Curvy moves if we talk about this most general surgery operations. So right, I'll connect it to this graphs in just a second. So I don't want to lose you, so I'll bear with me. We'll come back to graphs, and hopefully things will make sense. But
where does framing come in?
Oh, right. So framing is precisely this coefficient P over R. So in other words, for instance, if I have this picture of the trefoil, imagine that it's trefoil decorated by P over R. And if we talk about integral surgeries, then of course it will be just trefoil decorated with P, and we'll think about P as a framing. So, or its definition, we call P framing in this context.
But the question is where the graph comes from.
Oh, okay. Well, like I said, I'll come back to this in a second. But I want to make one remark, corollary from this theorem, once we have it right in front of us. that gluing is in this construction only needs to be done along the two torus. So in other words, only need, oops, that's the wrong color, in constructing general three manifolds. So for general oriented closed, I'm not going to write this again, three manifold M3, we only need cutting and gluing along two-dimensional tori, rather than most general Riemann surface. So this will be important later on when we'll try to upgrade this entire construction into TQFT. So TQFT in quantum topology is a way of constructing invariants of three manifolds and nodes by cutting and gluing operations. And of course, that's where we're heading. That's what we'll be going to do. And important, and in general, you're allowed to cut a three manifold along any codimension 1 and 2 manifold, but only genus 1 is really needed in this construction. So that's going to be extremely useful for us later, because we won't need to know what Hilbert space of this TQFT is on a high genus surface, which will be much more complicated. And even for genus 1, it will be extremely interesting, but this could be used as a bookmark for us to remember that we won't need something much more general. So now, right, so let me answer this previous question, how to connect it to graph, the graphs from the above. So I'll make another, so next point is relation of this statement, general theorem, to the above graphs, and now I can give them proper name. They're called plumbing graphs, or this construction is sometimes called plumbing construction. So let me explain it in a picture. So suppose you have a node or link K, which is representing, giving you the surgery of a three manifold. So basically, Jan, to answer one of your previous questions, see, even if we don't want to talk about nodes and links inside three manifold, in this surgery construction, they come in because node and link are giving you definition of what three manifold is.
Yeah, but I meant that if you have
in addition to this, yes,
in addition to this,
yeah,
probably
yeah.
you need to add representations of your quantum group.
Exactly. Yeah, so then there will be additional decorated components of node and link. That's right. So that's how I understood it, and it can be done. So maybe in the very end I'll be able to comment on it, but I wasn't planning to include this, because it will also cause confusion, in particular, since I'm using the surgery construction of the three manifold itself. So for us, therefore, from now on, you can think of three manifolds. So with abuse of notation, actually, let me do it right away. And write that three manifold, basically what it's going to be, it's going to be decorated link, or more precisely frame link, whose components are decorated by integers. So what would be typical example? So suppose you have something that looks like this. So I can create another opening here, and maybe just for fun, one more, or maybe two more, something like this. Okay, so that's good enough. So currently I have, oh, let's see. So this was This part of the figure is a little messed up, so let me fix it. Okay, here we go. So I have a link whose surgery coefficients need to be integers. So I have to write a1, that's an integer, a2 is an integer, a3. Here in the middle, I have a4, a5, a6, a7. So if I'm counting correctly, this is a link with 7 components. But as you can see, all of them are chosen such that they don't have intrinsic self-linking. So if I remove everything else and focus just on one of the components, it's actually unknot. So maybe I should have said that single unknotted loop, that's what's called unknot. Okay. So if you're in such situation when your link is constructed only out of unknots, there is not really topology of a knot to remember, and we can replace every component by a vertex. And every time it's linked in a non-trivial way, like on a Hopf link above, to another component, we'll draw an edge. So therefore, translation is that this particular example will be represented by the following graph. So for instance, here I have a vertex labeled by A2. It's connected to another vertex labeled by A1. So what's happening is components are becoming vertices of this graph called plumbing graph. So this will be A3. So then A2 is also connected to A4, which in turn is connected to A6. And A6 is connected to 5 and 7. So there is A5 and A7. So that's a particular example of a plumbing graph and how it encodes the data of the linking. Yeah.
I'm a bit confused. You had also this the matrix, which should probably something to do with linking numbers or what?
Exactly. Yes, that's exactly correct. So we had a definition of the matrix. Let's see, it was called Q. Yeah. So Q is which was adjacency matrix of the graph.
I don't remember you mentioned some equivalence relation on the matrices as well. So you had a graph with these markings, which were integers, but when you spoke about equivalence classes, the Q did not appear. So should it? Or it's automatic? I'm confused.
It's automatic. So Q is a partial information. So in general, if you have a non-trivial link with knotted components which are, for example, trefoil or something like that. So then this representation in terms of plumbing graphs in general cannot be done. So the link, therefore, is more accurate information. It encodes more, and that's all we need. So this link with integer decorations is good enough presentation of a 3-manifold. That's why I'm going to refer to such diagram. Proper name would be perhaps Curvy Diagram as a link, as a 3-manifold. This adjacency matrix is not going to play as important role in general as it played for graphs. For graphs, it basically encodes all the data. But you're right, under the smooths, even the size can change, as we saw, because we can create new vertices or delete some. And this indeed induces equivalence relations on Q itself. So it just goes along with different presentations.
I'm a bit confused because you said this by this theorem of Kirby and other people, there is a bijection between what homeomorphism classes of,
yes,
and some this combinatorial data modulo certain equivalences, but the matrix Q did not appear.
That's right, because matrix Q only appears in this special class of plumbed manifolds. I mean, that is also sometimes called graph manifolds. So in general, these Curvy moves are this theorem of Recursion-Wallace says that you can construct every three manifold by integer surgery on an auto link with these integer decorations. But then Curvy comes and says that this construction is highly non-unique, and you can have a number of moves which allow you, in general, actually, they modify the knot. So they can change the type of the knot and so on. So this come from, I mean, some of the moves are called handle flights, and I would have to explain a little bit more of topology to get to that, which I was planning to skip at least.
Yeah, okay.
For not very deep diversion into topology. So what we see here, or what we saw in this Kirby-Neumann moves, is how these moves are realized if link consists of unknowns and then can be encoded in a graph. But in general, one should not, in this picture that I'm currently sharing on screen, one should not work with right-hand side, which is the graph, but most general thing would be Curvy diagram involving non-trivial link, and then the proper moves would be called instead of blow up, blow down. Like some of them still would be called blow up, blow down, but there will be additional handle slides.
Okay.
So.
Does the graph with multiple edges between two vertices have a presentation in this link?
It can, in particular, but again, it's not really not going to be necessary for us for a reason that you already can anticipate. For instance, here, linking number between two components was 1. And that's why we're drawing single edge. So remember that vertices correspond to link components, and edge encodes whether they're linked or not. So you can imagine a situation where the linking number is more than 1. And then that would naturally correspond to several edges. Or you can try to make a link where you have now like a necklace. So there is a loop in the link, and this will correspond to a loop in the graph. So all of this in principle are allowed, but in general, again, this plumbing graphs give you only some subset of all manifolds, and you should work with this more general diagram. So I'll make an arrow and write it in green. So this is called, let's call it Curvy diagram. In other words, it's a presentation of three manifold. If one is really precise about details of topology, there is actually even underlined 4 manifold behind the scene here, which is non-compact, and the boundary of it is a 3 manifold that we're dealing with, and it's basically represented by nodes and links whose components are labeled by integers. So that's what we gonna use. Right, so I think our time is basically up for today. So maybe I'll just return to this statement of the theorem. There was a first bullet point which I didn't finish, and now I finally can do that. Oops. Let's see if I can scroll. This is theorem of Recursion-Wallace. These are definitions of Kirby-Neumann moves. Yeah, here we go. So, right. So what we now see is that we basically get some sort of invariant of Q-series valued invariant of 3 manifolds, because one can explicitly check invariance under this Kirby moves or Kirby-Neumann moves. And from the point of view of 3 manifold, this cokernel of Q is nothing but H1 of M3, the first homology. So later, it will be important to me that this group finite, or sorry, not finite, abelian group in general is isomorphic to the set of so-called spin C structures on 3 manifold. As a set, not canonically, more precise statement that we'll discuss maybe next time is that spin C structures form a torsor over H1, but as I said, they're of the same size. And therefore, what you can say is that now you get a bunch of Q-series invariants of 3 manifolds labeled by elements of H1, or equivalently, sorry, not equivalently, but better yet, spin C structures. So that's something that we'll discuss next time. I want to finish by going back to this bottom of the whiteboard by telling you where this plumbed manifold sit in the sort of Venn diagram of all possible 3 manifolds. So if this is the picture of generic 3 manifolds, so all 3 manifolds, then there are several special classes, which I'll discuss next time as also illustration. So one class, for example, consists of so-called Brieskorn spheres. Brieskorn spheres. These are homology spheres, usually denoted sigma P1, P2, P3, where P1, P2, P3 are coprime integers. I'll give you a definition next time. Today we're short on time. These are rather nice and special manifolds. They sit inside a larger class called ciphered manifolds. These are basically 3 manifolds which are fibered over 2 manifold with a circle fiber, which may have singular fibers, finitely many of them. And plumbed manifolds are roughly in between these 2 classes. They include all ciphered manifolds, all Brieskorn spheres, and a lot more. But they don't include all 3 manifolds. And again, I'll show you more examples coming back to this theorem of Recursion Wallace next time. And obvious goal that I now have is to generalize what I told you before to completely general 3 manifold, and also will naturally continue exploring the properties. So I apologize for running a little over time today. I think
it's fine. The only thing is, since you asked for the output of the audience, I can kind of give my output. Since I'm not an algebraic topologist, and you mentioned something about vertex operator algebras, quantum groups, and so maybe you will kind of include that part as well for those who wants to see the structures and do not want just to have a bijection between certain classes of 3 manifolds and certain integrals or whatever. So there is something more than just invariants of 3 manifolds. That's my understanding. And so you promised to give a bigger picture. So
yeah, that's right. Thank you. I'll definitely do that. Yeah. Probably already next time. Then, yeah.
So okay. So thank you very much, and so see you then tomorrow. Tomorrow you can have more time for your talk because it's a regular M seminar.
Well, I'll aim for maybe roughly hour 15 minutes, hour 20 minutes.
Yeah. It's up to you. Tomorrow is easiest.
In fact, yeah, I'll try to go maybe a little over an hour, leaving more time for questions. I think at this point, especially after tomorrow, it will be easier to start discussing, interacting more. So I'll leave quite a bit of time for questions, and some that I cannot answer immediately on the spot, I'll incorporate in the Friday's lecture.
Okay. All right. So thank you and see you tomorrow.
Yeah. Thanks a lot.